And it's a pleasure to have Marta Mazzocco, who will tell us about
triangulation, representations, and quantum algebra.
Yes, please.
I can speak fast so we can go swimming. No. So this topic, I don't know, it's not very much related to the conference. I don't think there is much gauge theory, but there is geometry. So I'm going to tell you about some algebras which are very interesting. They're called generalized double affine Hecke algebras. And I will want to discuss representations of these algebras. And for me, the motivation, I will give you also some motivation that I added the motivation just for Pasha because he told me, what, you're not talking about Pan-Levé? So okay, I add some motivation just for Pasha. But okay, so let me tell you what these algebras are. So what I'm going to do is to start with reflection, crystallographic groups. Okay, I hope this is nicely introduced. So I used to, since I moved to Spain, I used to what I call mosaics from the Alhambra. And so we have, I'm just focusing my talk on two of these groups. One is based on a square lattice, and you have the freedom of translation on the square lattice. And also you have a rotation. So, and the rotation, I don't know if it's visible. It doesn't change the mosaic, but I put two arrows here, and you can see that when you rotate, the two arrows are the other way around. And then the other one is instead a triangular lattice, and you have now translations and rotations of 2 pi I over 4 pi over 3. 2 pi over 3 and 4 pi over 3. So, okay. So these are two nice groups, and you can represent these groups in a slightly different way, which I prefer. So you can introduce some generators, which, okay, so I'm not going to go on the board and show you that these 4 generators that I wrote here, you can express in terms of these guys, and these guys can be expressed in terms of these other ones. But what I like about these other generators of the same group is that they are reflections, so the square of each of these generators is 1, and then the product is also 1, okay? And the same here, you can introduce now 3 generators, which also not reflections, but the cubic power is 1, and the product is 1, okay? So we have two groups, which, and I've given you the presentation of these groups. And now I would like to quantize these groups and also deform these groups. So first you quantize and then you do what is called a flat deformation. But it's going to be fairly simple, so don't worry about it. So what do you do to quantize? First of all, let me remind you, so essentially each of these groups, you see, you have a lattice, is the Z2, and then you have something acting on this lattice. Okay. So we want to quantize the lattice. Okay. So to quantize the lattice, first of all, well, you cannot really quantize the lattice, at least maybe you know how to do this because but I don't. So you create an algebra out of this lattice, which is what is called the group algebra. So essentially what you're doing, you're saying, okay, I can imagine my lattice to be given by n and m, and I think about x to the n and y to the m, okay? So it's very simple. So what you see is, oh, I keep making mistakes here. So you can imagine that this lattice, roughly speaking, is a torus. Okay, well, that's very simple. Also, you can imagine it geometrically. If I have a square lattice, I identify the opposite sides twice, and then I get a torus. It's the same idea, okay? And then you quantize this torus. So torus is also the same thing as the ring of Laurent polynomials in 2 variables. And then when you quantize, so when I have Laurent polynomials in 2 variables, you know, these 2 variables belong to C in my head, so, you know, they commute. But when I quantize, they stop commuting. So you put a Q, and you define what is called the quantum torus. And now what you want is to go from what we had before to something quantum. And in this case, it's lovely because you just plug a Q. Oops. You just essentially, you remember we had these relations with remain the same, but then the product just instead of being 1 now is Q, and in the other case also. Okay? Is any problem here? No? Okay, so this is just first the quantization of the crystallographic group. And now I want to tell you what is a Hecke deformation. So in two cases, okay? So we have that in the first case, the relation k squared, each of the generators squared is equal to 1. This is the same as saying, I hope that this I don't have to explain, that the product of k minus 1 times k plus 1 is 0, okay? And in the second case, we have that the cube of a generator is equal to 1, and then this is also equivalent to this relation. So what is a Hecke deformation? A Hecke deformation is that you want to change these scalars, okay? That's all what it is. So you want to have an algebra now in which you replace these relations by something in which you're allowing any eigenvalues. So from the quantum crystallographic group, we obtain something similar in which for each ki, I replace the ki equal to 1 with a relation with some ti, which are now scalar, okay? And in the case of the ji's, we also replace these eigenvalues by some scalars. That's all. And I should say that for reasons which will be probably a bit mysterious, but because we will want to relate these two guys, we have chosen a strange normalization of Q, so I replace the Q of before with Q to the minus 1/2 and the Q here with Q to the minus 1/3, but this is just technical.
So shouldn't it be plus in one of the brackets, like K minus K?
Well, I prefer to write it this way. You can, in the Daha case, certainly, but you can do I can take imaginary time. Yes, it will be hopefully clear soon why I want to put them in this way. So in this case, this is called the double affine Hecke algebra associated to C1 check C1, and it was introduced by Cherednik and generalized to higher rank by Sahi. And this case is actually called generalized double affine Hecke algebra, was introduced by Ettinghoff, Blonkov, and Reins, and then they also introduced higher rank. But for today, I'm discussing rank 1. So what I'm going to do is to discuss representation theory of these guys, okay? And what I want to now give you some motivation why I should care about this stuff, apart from the fact that, Ettinghoff and Reins, I never met Oblonkov, but Ettinghoff and Reins are very funny guys and I like them. So, I should try to work on something nice, but there is also mathematical motivation. Okay, so, so essentially, these generalized double affine Hecke algebras appear as related to affine Dynkin diagrams of star shape. What does it mean, star shape? It means that you have a center and from it some legs irradiate out, okay? So I've drawn only two cases, the D4 one, which corresponds to the Daha, and the E6 one, which corresponds to this second example I've been talking about. There are another two, which I haven't drawn, and because actually we haven't yet done anything with them, but hopefully what we do will apply to that case too. And okay, so already when I start seeing Dynkin diagrams, I'm very happy. But there is something even more interesting that you can study the limit as Q goes to 1 of these algebras. And then when Q goes to 1, you find that they have a center. What it means, they have a set of elements which commute with everything, okay? And this center is actually described by some curve. So algebraic variety, which is like what I wrote here, these two. So let me maybe just say a few things here. We have an algebraic variety, an affine, sorry, I should have said affine variety, written in three variables, x1, x2, x3, which satisfy one relation. And these omegas here, they are related to these TIs by some formula, which you don't need to know. And similarly, for the G-Daha, you have that also when Q goes to 1, there is a center, and differently, here you have just these quadratic corrections. You have cubic, cubic, quadratic. Then there is some epsilons and some omegas. And actually also these epsilons and omega are functions of the T which belong here. So everything is quite clear. And excuse me?
What's the axis? X1, X2, X3.
So okay. Yes. Right. It's the limit as Q goes to 1 of certain elements in the algebra. And these elements, when Q goes to 1, become central. So what quantistically, I will show you now a formula. So quantistically, you will have some elements in each of these algebras. So let me take this D4. Okay? And these guys define a subalgebra inside the Daha, which is called a spherical subalgebra. And when you go, as Q goes to 1, then the spherical subalgebra becomes this affine object, which is endowed with a Poisson bracket. And that's what it happens. Now, for the G-Daha, for the Daha, we know exactly what the xi's are, okay? So the capital xi's, whose limit is the small xi's. For this one, no, we don't. So the way that Etigon, Voblonkov, and Reins cooked this cubic surface is completely, it's not direct. Let's put it this way. But okay, so for me, the motivation was trying to understand these two algebras a little bit, because this cubic appears in the theory of Pan-Levé equations. And so I was curious to know whether or not this cubic also appears in the theory of Pan-Levé equations. And so let's see. And so, as I say, so this was my motivation slide for Pasha. So this is the monodromy manifold of the Pan-Levé 6. And what about this? I don't know. Okay, so this is the question, and I'm not going to answer this question, okay? So, sorry. But at least it motivated some work. And what will the work be? I will tell you now in a second. So I want to give you this diagram, which is a famous diagram by Sakai, in which he lists the Pan-Levé equations in an awkward way. So we have here Pan-Levé 1, 2, 4, 5, and 6, and here we have Pan-Levé 3. And these they are listed according to the singularity type they have, but doesn't matter. The point is that Sakai classified all the second order possible ordinary differential and Q difference equations according to certain rules, let's say, which should be the whole family of Pan-Levé equations, at least in order 2. And he also classified the confluences between them, okay? And so if I have Pan-Levé 6, which I should have, because this is my monodromy manifold of Pan-Levé 6, I can only go to Pan-Levé 6 from two directions, from this guy on top and from this guy on the left, okay? And so with Nalini, Joshi, and Peter Roffelsen, we studied the monodromy manifold of this guy and say, okay, this is not going to give the cubic I'm looking for, okay? And there is a good reason for that, because this guy, the bottom, at infinity. So if I maybe where is it's behind you. Okay. So so this is an affine surface, but I can make it projective. The way you can make it projective is simply saying, okay, this corresponds to the point 1, x1, x2, x3. So if I now do a change of variable and I want to put it in coordinate, I don't know, projective coordinate z0, z1, z2, z3, then effectively what you're doing is multiply all the non-cubic term by z0. Okay, it's not very difficult. Okay, so I will write this. I'm sorry for the people who are sitting there, but I'm not going to write it twice because I'm going to go crazy. Oh, sorry. Okay, plus z cube 0 omega 4. So you projectivize, and then you can look at the other chart. So this is the chart where z0 is equal to 1. Now I look at the chart where z0 is equal to 0. And what that gives me is that I lose all these terms, and I left with the z1, z2, z3 equal to 0, which is 3 lines in projective space. Okay, so this configuration here is this. And for this one, because you have x cube 3, x1 cube, and x2 cube, the configuration at infinity is going to be a degenerate elliptic curve. And what we did with Peter and Nalini was to show that instead for this equation at infinity you have a non-degenerate elliptic curve, so there is no way you can do this. Okay, so this is not that cubic that I'm chasing is not coming from here, and then maybe it's coming from here. So this is, I haven't had yet time to study this, but I would very much like to understand. In any case, maybe
this is completely obvious, but the confidence limit is supposed to act by 2 in the omega?
Not only. You also change the axis. See.
But that doesn't affect your argument about this behavior.
No, it does. So what I was trying to say is that, okay, so this guy has 3 lines. This guy has a degenerate, and this guy has a standard elliptic curve. So if it is true that I can confluence this cubic to that cubic, I should be able to confluence the divisor from the degenerate elliptic to the triple of lines, which I know I can. But unfortunately, the candidate that I have on top is already a little bit confluenced. So maybe that cubic is coming from here, then going here. I don't know. So that's what I'm trying to say, that I don't know where to place it. Okay.
What is the relation between the symmetries you have in the Sagai diagram versus the symmetries you have for this cubic with Data and Theta? Are they just the same? Because then it's kind of obvious that d phi 1 does not fit d phi 1.
Okay, so the symmetries is a complicated question. So that's also another line of research that I started recently with Tom Corvinder. And we are trying to understand at the moment, so we are, we're just here, and we are just trying to understand, or in other words, classify all the automorphisms of the Daha, okay? And these are coming from the symmetries. So we haven't yet tried to understand how to classify. So it's all a little bit.
So my only point being that the viral group D41 that you get for the algebra,
Mm-hmm.
is it not just the D41 and the basics?
Yes. Yes. So that's why I'm hoping that, I was trying to find this E61, and so, I don't know how to use this. So, but you see that I have two E6s here. That's the problem, and I don't know which one to pick. Practice. I think bottom one too. Yes.
My question ties into this. So what are these orange? Those were not Sakai.
No, they all in Sakai. Oh, yes, sorry. This is elliptic. The blue are Q difference, and the orange is standard difference.
No, the red ones are standard difference.
No,
The orange.
all standard.
The orange. I mean, I had different ones like here.
Yes.
The orange were not there. So like, are there?
They are there. This is taken from, there are two pictures in Sakai. Look. Anyway, yes, I will show you later.
There are ways to find them.
Yes. I mean, Sakai paper has to be, every so often you should read Sakai paper. I keep.
I mean, I understand the.
If you want to find something, you can look at the one no media mark.
Yes. Yeah, I agree.
Probably something we have system was singularized. Yes.
Okay. No? More? No? Okay. So what have I done instead? So to start so this was my motivation, and it's a motivation that has led me for several years to do different things, shall we say. And this today I'm telling one of these things. So what I wanted to understand, if there is any way that I can take this generalized double affine algebra and specialize maybe the parameters in such a way that I can prove that it's that there is a bijection with the Daha. Okay? So I want to see this one inside here as a special case. And that's what I'm going to tell you today. Okay? It's not very simple, but it actually do. Okay. So what I'm going to do first is to tell you a little bit how to give representation theory of these two objects. Now, the representation theory of this Daha is known since zillions of time, and it's in terms of co-difference operators. But I was not interested in that. I wanted some more natural representation for me in terms of matrices. Okay? And the same here. I want to give some representation in terms of matrices. Okay, so let me go. I forgot to tell you this. Okay, well, maybe I don't need to. Okay, so what I want to do is to create some reduction operator which maps this E6 kind of generalized double affine algebra to the D4 double affine algebra. And to do this, I first need to do some representations. Okay, and to do the representations, what I'm going to do is to study triangulations. So why, you may say, why on earth do you have to triangulate something? Well, first of all, because triangulating is fun. But secondly, because in fact, if you look at these equations and with some fantasy, you see that there is a Riemann surface staring at you very, very clearly. Why? Because what do we have here? If I'm looking for a matrix representation, well, what I have is that each matrix should have two eigenvalues. Okay, so it's already telling me SL2. I'm here. I'm SL2. And the second thing is that normally, if I think in terms of a Riemann surface, then these guys will be four monodromy matrices around some holes. Okay, so this is telling me there is a Riemann surface, which is sigma 0, 4, so genus 0 and 4 holes. And then this case will be some monodromies, at least when Q is 1, okay? And the other one, it's telling me instead that I have 3 eigenvalues, so now I have SL3, and I have 3 of these matrices, so they will be on a Riemann sphere which has only 3 boundaries, okay? So the basic idea is, okay, I know these spaces quite well. They are character varieties, and character varieties, well, generalized character variety because you have holes, but it doesn't matter. But you can coordinatize this by Fock-Goncharov coordinates, which quantize. So here you go. I study the Fock-Goncharov coordinates on this Riemann surface and on this Riemann surfaces. I cook up my matrices, and then I quantize using the Fock-Goncharov procedure. This is essentially what I've done. And I should say that the first part I've done on my own, and the second part was the work of one of my PhD students, Davide Del Martello.
Quick question. Maybe you're going to say this later, but when you do this and you think about Fock-Goncharov, right? So this Q is the deformation parameter, the quantizing Fock-Goncharov. Is it the case in the Fock-Goncharov case that when you take the 4 monodromies or the 3 monodromies, they don't add up to identity, but actually to Q?
Yes.
Oh, okay.
Yeah. So if you quantize, yes. If you don't, no. Yeah. Yes, that's the point. And that's why we also take these stupid Qs, because we wanted the next step after I studied the representation theory will be to take some limit of this guy and get this guy, and I wanted the Q to be the same. Okay. Anyway, okay. So maybe very quick crash course on Fock-Goncharov theory. Okay. So in general, you consider representations of a Riemann sphere or a Riemann surface of genus G and S holes, as in the tradition of Chekhov and Penner. The number of holes is always S because you like to be vulgar. Okay. So anyway, right. No, nobody got it. No, because I was giving a talk in Cambridge, and I said, and I take a Riemann surface with S holes, and then I look around the room and people went blank. And I thought, oh my God. Okay. Anyway, so, yes. And there were many of them in the audience in that occasion, but okay. Yes. Okay. So anyway, what do you do to have representations so you're taking representations of the fundamental group into generally PSLM, and then you quotient. So what do? You divide your Riemann surface into triangles, and then you associate a quiver to each triangle, and the quiver you associate depends on the dimension on the rank of the group in which you are doing everything. So in the case when M is 2, the quiver is just another triangle. In the case of M equal to 3, you have an hexagon. Okay, never mind. And each of these quivers is endowed with some variables which satisfy, in the classical case, Poisson relations, and in the quantum case, they satisfy some quantum relations, and the quantum relations are dictated by the quiver. So, for example, here I have an arrow from this guy to this guy. This means that, so if I call this zeta alpha and this zeta beta, then the commutation relation between them is given by this relation. When there are some dashed arrows, and in those dashed cases, you instead of a q minus 2, you have a q to the minus 1. And when there are no arrows, then the variables commute. Okay? So, okay. So, from each triangle also, using these variables, you construct what are called transport matrices. And these transport matrices, there is a technique to construct them. It's called, people call it snake calculus, plumbing calculus, whatever. In any case, I'm giving you just a recipe for T1, T1 is this guy. Is constructed of those coordinates, and in the 2 by 2 case and the 3 by 3 case. So you can see that it's a little bit heavy, okay, but the advantage is that you can put it on a laptop and press return, okay, unless you have done mistakes, the answer will work. So it's a bit heavy, but there is a huge, computationally it's great. So anyway. So what do you do now? You triangulate your Riemann surface, and then you have some paths or loops, and you want to represent this path of loops. So what you do is that it will go through triangles, and therefore it will be decomposed in TI matrices, each from each triangle. Okay, so roughly speaking, I will give you a picture. So this is the graph of the case D4. So we have a Riemann sphere with 4 holes, 1, 2, 3, and the outside. So we triangulate, and then I have some loops, for example, this yellow one, okay, or we could have a complicated, the green one. So for example, the green one will be T1 on this triangle, then I'm going to do T2, go around, T3, and then again T1. Okay, to the -1. So if you endow everything with coordinates, which are described by the quivers, which are inside these triangles, then you can decompose your matrices. There is a second operation, which is called amalgamation, that when two sides are attached, then the variables multiply each other, but that's not a huge problem. So you have a practical way to construct your matrices, and so here I've written all the matrices that are interesting for us. So they are color coordinated: O for orange, B for blue, G for green, and pink for the one which goes around everybody. And as you can see, they are products of these T's. There is some S matrix that just reverses the orientation. But we have a right triangle, a central triangle, what was down triangle, and a left triangle. Okay, so just anyway. So the point is that you can show that this gives you a faithful representation. Once you quantize, you have a faithful representation of this Chidaha. Okay.
Depends on the choice of base point.
Absolutely. So if you change the base point, or in other words, I change where to break this stuff, I will get a different representation. And this opens a can of worms, okay? There is no Laurent phenomenon here, by the way. No, because Laurent phenomenon will be only for the invariants. So if you take the traces. But here I'm really using matrices. So I'm looking at the entries. And these entries are nasty, okay? But okay, and in fact, we don't do cluster variety. We just do a cluster chart. We don't want to, it's enough. For me, it's enough to see everything, so it's okay. So in the same way, I will, now we have chosen a different, in this case, it's a Riemann sphere with 3 holes. So one, this one, 2, and the one outside, and you can play the same game. I'm not going to show you. But then you can construct these matrices with their amalgamations, and there are some fairly excruciating formulae that I haven't written down. But again, this formula you can put on a computer and say calculate with the commutation relations, and the computer does it for you. Of course, to reach the point in which you can actually do that, you have to work a little bit, but okay. So these are, and again, we have some representation. So now what I want to do, okay, I want to understand. So I take this representation and I want to cook out of it a 2 by 2 set of 4 matrices. Okay, so I have 3 matrices which are 3 by 3. And out of them, I want to cook 2 by 2 matrices by some procedure which makes sense, not just, Okay, and so this procedure is actually Katz-Middle convolution. Now, Katz-Middle convolution is, I think it's, okay, I don't know how much people know about Katz-Middle convolution here, but not much. So suppose that, so Katz was interested in the concept of rigidity. What is rigidity in a differential equation, right? Say you have the hypergeometric equation and you calculate the monodromy. And then you ask the other question. If I give you the monodromy, can I reconstruct the equation? Rigidity means that the answer is yes, namely that, or in other words, that you can do it only looking at the local monodromy, or in other words, at the Riemann symbol of your equation. Is that making any sense for anybody? Okay, thank you. So you don't have what are called auxiliary parameters that you have seen in the Hoyne equation, in many other equations, okay? So rigidity is the absence of auxiliary parameters. You have your local monodromy, and that's enough to know everything about your differential equation. So Katz was interested in rigid differential equations, and he cooked a procedure to construct from one rigid differential equation another rigid differential equation. And there is a beautiful long story which is actually related also to do some sort of Euler transform between these equations, that essentially, or what is called fractional derivative, that you would like to take some equations, you take the solution, and then you take the fractional derivative of this solution. This will satisfy another equation. So the idea was to classify equations, and he came up with this scheme. So this is what we are going to do now, and we are going to use this Katz procedure. And so the idea is that we take some representation of our matrices. So now of our generalized of the double affine algebra. So these are K1, K2, K3. So this case are 2 by 2 matrices. And out of it, you cook a bigger matrix, okay, for 3 bigger matrices, which are 6 by 6 now. And then you want to make some projections of this, because this is too big. You want to in some sense, eliminate all the freedom you may have. And there is some projection you can do. And out of this, essentially what happens is that you look at you project these matrices, all of them. Okay, so let me try to say, this is 6 by 6. And I want to project them on the space in which I have, say, V1, V2, V3. And this V is an eigenvalue. V1 will be eigenvalue of K1. V2 will be eigenvalue of K2. And V3 eigenvalue of K3, in which the eigenvector is equal to 1. So actually, I should have rescaled my case in this slide, because maybe you remember that my eigenvector. Oh no, I think I've done actually. Sorry. No, I have rescaled everything. Sorry. So I take V1 to be eigenvalue with eigenvector with eigenvalue T1. V2 to be eigenvalue with eigenvector with eigenvalue T2. And V3 eigenvector with eigenvalue T3. Okay, so you do a projection, and what this allows you to do, we have 6-dimensional space. We have you're reducing by half. So essentially, you find some matrices R1, R2, R3, which are 3 by 3, and they are essentially reflection matrices. And then you do something which is also quite standard in algebra. You do killing factorization. You take the product and you say, I want to consider this product as the product of an upper triangular matrix and a lower triangular matrix. And essentially, you manage to cook out of this procedure. You cook from the representation of your double affine Ecke algebra related to the Riemann sphere with 4 holes and 2 by 2, you construct a representation of your generalized double affine Ecke algebra in terms of 3 by 3 matrices. So this is essentially the theorem that we, I went so fast trying to, because I felt, it's done almost, it's almost done.
This is very good.
Sorry. So this is maybe tiny step, okay, that we have done, was to trying to understand in how many ways I can reach this, the motivation for me is in how many different ways I can try to reach this Pine level 6, but when I do it on the level of these quantum algebras, then you find something interesting regarding this generalized double affine Ecke algebras and standard double affine Ecke algebras. And in particular, the representation theory for the J-Daha is not really complete. There have been several examples of representations, but they specialize the parameters, whilst these matrix representations that we found are for generic parameters. So you can do really everything with this four culture of coordinates, and which in a sense facilitates your life, because, for example, to answer the previous question, what are X in the case of this generalized double affine Ecke algebra, you may have some idea, which we did. I had some idea, X should be this, try, nope, wasn't that. But at least, now I can compute. So I think X is this, no, doesn't work, okay, do some more thinking, okay. So a little bit of an outlook. So, well, first question is whether we can do higher rank, or also the other J-Dahas, which Blankov, Ettinghoff, and Reins introduced. And also, if you manage to do this, then I think that these affine varieties that arise as limits as Q goes to 1 as centers may be interesting on their own right. Maybe they have some properties. For example, the two I've shown you, when you quantize them, they give you some Calabi-Yau algebra. It's interesting. They may appear in mirror symmetry and so on. And as I said, the motivating question is how do these fit the Pan-Levé equations? Is there any way that I can see this stuff? Or maybe I need to go to higher order Pan-Levé equations. I don't know. But anyway, this is all. Thank you.
I see Marta is eager to swim, but we still have a few short questions.
So I have two questions. First is, did you try the same? So you went from the character variety to the monodic representation of Riemann surface. Did you try to do this at the level of QP6?
So in the level of QP6, so the QP6 isomonodromic problem was studied by Joshi and Roffelsen, and what they did was to show that so in that case, when you write the Q difference problem, the Q difference problem has two singularities, one at infinity and one at 0. And as you know very well. And then you can define, instead of monodromy, you define a connection matrix, which we relate this local solution at 0 to the local solution at infinity. And what they did was to extract some affine variety out of this study, which is an embedded variety in C6. This is the Segre surface, okay? And then what we did was to try and see whether we could, first of all, the first computation we tried was to see if there was any way that we could write this as a nice cubic surface. In some sense, and I insist on nice, because any Segre affine variety can be written in a cubic way, but it will not be nice. Okay, so nice means that somehow repeats the form of these ones that I've shown. So that was not successful. Then we thought, okay, let's take the limit as q goes to 1 of this Segre. And what we found was another Segre, which is for Pine level 6. And for that, we managed to construct a map to the cubic. But we cannot, at the moment, we haven't been able to lift this map to the QKs.
So the follow-up question is that in the other, in the generalized data setting where you still get a cubic, you have a very well-defined cubic surface there, which is going to be 3 punctures, but it's SL3. So does this not mean that the right candidate should be like a SL3 hypergeometric as opposed to additive?
Yes. There is also a problem with that. Because yes, this is actually not nice. This is something I've been thinking. Okay, so the main problem is that Harini knows something that you don't. So Harini knows that for Pine level 6 we have at least two isomonodromic problems for Pine level 6, right? One is maybe not only Harini but several people know, but anyway, one of them is the standard Fuchsian 2x2, and one of them is what I call Dubrovin system, which is a system in which you have 3x3 and it has a simple pole at 0 and a double pole at infinity. So these two are related to each other with, in fact, middle convolution. So I was swiping this all under the carpet. Okay. Now, the main problem is that I haven't come up with a good way to confluence a 3x3 hypergeometric system to this Dubrovin system. The main reason being that when I confluence, so if I take a system of this form, say I will take, I don't know, A0, Z, well, minus epsilon, say, plus A, T, Z plus epsilon plus A1, okay, Z minus 1, epsilon. So I could try to send epsilon to 0 and create a double pole. What we proved with my other PhD student, Ilya, is that then this will lead to something which, let's say that, I will write it in this form, in which, okay, so I should have put, maybe, let me put a tau here, in which I have tau that multiplies a matrix, maybe constant matrix, doesn't matter, okay, plus another, maybe I1, I haven't really cooked up this very nicely. The point is that the tau will be the new isomonodromic time, and it appears as multiplying the entire matrix at infinity, which means that you cannot have that the eigenvalues at infinity move relatively to each other, which is what instead is the isomonodromic problem for Pine level 6 in the 3x3 case. So I don't know yet how to do this. And I think that we don't need hypergeometric. We should have something more. And I'm still thinking what. And okay.
But back to geometric, this cubic root is just manifold for just 3 puncture spheres. So there is a 0 and a 1 and that's all. And this and corresponding difference equations are just Beckman transformations of this 3x3 system. Probably they are written in this form somewhere in Gemini's paper. Or,
okay.
So it's just this 3 puncture system.
So maybe that's what, yeah, I haven't really given it much thought.
I don't know where precisely in the converter 6 in the system, like how to take the limit properly, but if it is described somewhere, then well, this conferences I described in some papers.
Yes.
It is a bit trickier to take confluence.
Yes. Confluence is tricky business in general, but yes, I mean, if you have any ideas or something that the problem is out there. Okay.
If you want, can you also say something about the slide that you skipped?
Oh no, this is okay. Sorry.
Marta was running fast, and now all this time you are doing it.
Okay, so yes, so here what I've done is simply to tell you this. So I told you for q equal to 1, the center is given by these two surfaces, and so now what I've written in the next slide that I'm going to show you is I take these two surfaces, I define a Poisson structure on them and quantize. And so this we did with Chekhov and Rubtsov. So anytime you have a polynomial of 3 variables, you can define a natural Poisson bracket by taking the Jacobian. This is called Nambu bracket. And then it has a beautiful property that this phi by which you define the bracket itself is central. So it will commute with everybody else, which means that you can restrict your Poisson bracket on the surface, okay? So each of these surfaces is automatically endowed with a Poisson bracket, and then you can quantize this Poisson bracket, and this we did with the Chekhov and Rubtsov, following a procedure by Ettinghoff and Ginsburg. And what we found is that you can quantize it very nicely. You have an explicit quantization of this bracket. And okay, so so I've written kind of unified expression here. If I want, and with a mistake, oh, lovely. So actually this Q1 over Q and lambda should be swapped. Okay, I'm really sorry. This should go there and that should go here. And then when lambda 1 and lambda 2 are 0, essentially this gives you the spherical subalgebra of the double affine algebra D41. So conjecture is that this guy for lambda 1 and lambda 2 different from 0 is the spherical subalgebra in the generalized double affine algebra. Problem. I have no clue how to write these x's in terms of generators in the generalized double affine algebra. Okay, so I know what x is in terms of in the standard case, but I don't know what it is in the general case. Okay.
At least in the commuting case, there are cases of
Yes. So this this in the yes. So this trace is nothing else than so essentially in the Daha case, you introduce some multiples. So it depends. First of all, what do you do to do the spherical subalgebra? You select one idempotent. For example, I can select the one corresponding to K1. What does it mean? That out of it I cook something E. Let me maybe something like this. I don't remember really E, and then you should have that E square is equal to E. But please don't take this constant as they will be wrong. Anyway, so you do this, and then you cook some x1, which will be k1, k2, plus k2 minus 1, k1 minus 1, and then x2 will be, I don't know, k1, k3, plus the other way, and then you find that if you take the projection of these on the sorry, let me put a hat, and then I define xi to be E xi E, then these guys generate the Daha. Okay, and then they satisfy this with the lambda equal to 0. But for the GDAH, I don't know how to do this. I was trying to use the middle convolution to guess, right? Because I know I can see the D4 inside. So maybe if I apply the middle convolution to the axis, I can see what happens, but this didn't lead to anything decent. Yeah.
Okay, I think we will
Sorry.
stop here.
Yeah.
If you have more questions for Marta, I can provide her coordinates for coming to ours, but otherwise, let's leave Marta. And we meet